And the last section we want to cover before we start working on a simplex method is what is called as elementary row operations on linear equations. So let's say that we are given a system of linear equations. So we have ax plus by is equal to e and cx plus dy is equal to f. So what we can do is that we can represent this linear equations as a matrix. So we have row 1, row 2, and the coefficients of x and y are a and b, and in row 2 it's c and d. The right hand side values of constants are e and f. So we can represent this as a matrix which is a, b, e, c, d, f, and just for our reference we can put a title x, y, RHS and r1, r2 as the row. Now there are two operations that we want to always remember, and these two operations do not change the solution set for the system. So if we multiply any equation, or in our case of the matrix, any row with a non-zero constant, then the value of the solution of those system of linear equations does not change. And same thing with operation 2, that if you add or subtract any other equation on row with an equation on row, the value of the solution will not change. Let's take a quick look at an example and then we can see what these two operations are. What does this actually mean to us? So now we are given a system of linear equations 2x plus 3y is equal to 10 and 3x plus 2y is equal to 5. So the first step is converting it to a matrix form. And what we are going to do is we are going to label x, y, RHS and r1, r2. So r1, r2 are the rows, x, y, RHS is the x column, y column and the right hand side column. So we have 2 from 2 as the coefficient, 3 as the 3 coefficient of y if row 1, value of the right hand side 10. Similarly 3, 2 and 5. So now what we are going to do is we are going to assign the value in row 1 as whatever is the current value of row 1 and multiply it by 3. So if we multiply row 1 by 3 and then substitute that in this matrix, we get 3 2s are 6, 3 3s are 9, 10 3s are 30. And then similarly we multiply R2 with any non-zero constant and substitute it in the new matrix. It should not change the values of the final solution. So in this case we are saying 3 times 2 is 6, 2 times 2 is 4, 5 times 2 is 10. So again repeating, what we did is in the new matrix we multiplied row 1 and multiplied it with the constant 3, and then in the row 2 we multiplied it with the constant 2. Both of them are non-zero. Now let's take a look at another operation. In this step what we will do is we will pick up the last matrix form and we will say, okay, the new value of row R1 will be the value of R1 existing minus the value of R2. So in this case we are saying the new value of row 1 will be 6 minus 6, which is 0, 9 minus 4, which is 5, 30 minus 10, which is 20, and then we say, you know what, we are not going to change R2, we will just leave it as is. So we say 6 4 10, 6 4 10. Okay, let's see another set of an ERO, which is elementary row operation. We will change R1 to R1 by 5, and what we are doing is 0 divided by 5 is 0, 5 divided by 5 is 1, 20 divided by 5 is 4, and again we are leaving R2 as is, 6 4 10, 6 4 10. And in this ERO we are going to do is we say R1, I'm going to leave R1 as R1, but for R2 I'm going to assign it the current value of R2 minus 4 times R1. So we say R1 is same, but R2 becomes 6 minus 4 into 0 is still 6, 4 minus 4 into 1 is 0. 10 minus 4 into 4 is 6 minus 6. So we get 0, 1, 4, 6, 0, minus 6. And in the final step, we say R1 stays still R1, but R2, we will assign it the value of R2 divided by 6. So 6 divided by 6 is 1, 0 divided by 6 is 0, minus 6 divided by 6 is minus 1. What we have done by performing these steps is we have actually solved the set of linear equations, and y has a value of 4, and similarly x has a value of minus 1. So if you would solve this problem, you will get the same answer, that y is equal to 4 and x is equal to minus 1. And this method that we saw is called Gauss-Jordan elimination, and as I said, this method actually solved the system of linear equations, and we got y as equal to 4 and x is equal to minus 1. So what we have done is essentially we have taken steps, in this case 6, to systematically reduce the left matrix into a identity matrix, and then by doing so we were able to identify the solution of each individual variable. And one thing you may want to notice is that the series of operations generally is always involving the same row, or in the second ERO we are assigning R1 the value of R1 multiplied by a constant, R2 the value of R2 multiplied by a constant. Again, in ERO3, R1 is assigned a value based on the previous value of R1, subtracting the value from another row. Same thing here, R1 becomes R1 by 5. Same thing here, R2 becomes R2 minus 4 times R1, and R2 becomes R2 divided by 6. So the bottom line is that each row performs an operation on the previous value of its row, and the operation could be a multiplication of a constant or a subtraction or addition of another row multiplied by a constant. So finally, I just want to introduce one terminology. So consider a system of linear equations which is x1 plus 3x3 minus 2x4 plus x5 is equal to 10, and here we have x2 plus 2x3 minus 3x4 plus x5 is equal to 5, 12x3 minus 2x4 plus x6 is equal to 15. In this case, we have x1 and x2 and x6 have zeros in all but one equation. So x1 is 1 in only row number 1, x2 is 1 in only row number 2, and x6 is 1 in only row number 3. Such a variable are called as basic variables. And another thing to notice is that each equation has at least one basic variable, and having one basic variable in each equation, we will term it as canonical form. In this case, we did not have to perform any elementary row operation to bring this set of equations into canonical form, but you can perform elementary row operations to convert a given system of linear equations into canonical form, and these operations are called pivot operations, and that is the basis of simplex method that we will see next.